These grains of sand remind me of the stars. They're in a one-way flow with no turning back. The universe is slowly emptying like a giant hourglass. Stars are born, they shine, and then they fade out. Galaxies are moving away from each other. Sometimes I feel like we're close to that last grain of sand. This feeling isn't foreign to physicists either, because the laws of nature always tell us the same thing. Energy dissipates, it gradually weakens. Order gives way to disorder. This is entropy. But right here, there's something strange. As the universe's sands flow down, an invisible hand seems to expand the hourglass glass. The universe is expanding, accelerating without stopping. So how long will this go on? Will it just keep expanding forever? Or will everything reverse at some point? When we first start blowing up a balloon, it inflates very fast, right? Because our breath is still very fresh and very strong. But after a while, as we get tired, that strength starts to decrease. Naturally, the inflation rate slows down too. Well, in the universe, the exact opposite is happening. The expansion rate is constantly increasing. Far from weakening, the universe's breath is getting stronger. It's as if a hidden force is constantly boosting that breath's power. Until 1998, we had no idea such a force existed. But that year, a discovery changed our view of the universe. Astronomers measured the brightness of supernovae in distant galaxies and found something unexpected. They appeared much dimmer than expected, meaning they were moving away faster than predicted. This meant that the universe was expanding at an accelerating rate. This sent shockwaves through the scientific community, because until then, the consensus was, yes, the universe expands, but that expansion should slow down over time. Like the weakening breath example I gave. Here, gravity should have slowed everything down. But an invisible force was constantly pushing the universe. Scientists called that force dark energy. I've tried to explain it quickly, but this discovery even won the Nobel Prize in Physics in 2011. So we're talking about an event that's that significant. To explain this incredible acceleration, astrophysicists brought up an idea Einstein once called his biggest blunder, the cosmological constant. In its simplest terms, this means the energy of empty space itself. And for a long time, they assumed the amount of this energy never changed, acting as a force pushing space outward. This detail is important because a new study, which I'll explain and is the main topic of this video, questions that very assumption. While gravity pulls the universe inward, dark energy, which makes up 68% of the universe, pushes outward. So these two forces are in a constant state of struggle. But because the power of dark energy is greater, the universe continues to expand constantly. Now, this is our standard model of cosmology. According to this model, the fate of the universe is clear. Even though dark energy is constant, the universe will continue to expand at an accelerating rate. Because as it expands and creates more space, more repulsive energy emerges along with that space. Consequently, the universe is expanding faster and faster. This standard model leads us to a fate that isn't very romantic. Yes, the big freeze. In other words, within an expansion that lasts forever, the universe is becoming colder, darker, and lonelier. Just a few weeks ago, a study was published that further strengthens this theory. Scientists examined data from the European Space Agency's Euclid and Herschel telescopes. Do you know what they saw? That star formation is gradually decreasing. The research team conducted the most comprehensive temperature measurement of the universe to date. By analyzing the infrared radiation of 2.6 million galaxies, the temperature of stardust was measured. According to the results, it was revealed that the temperature of galaxies has cooled from an average of minus 238 degrees to minus 248 degrees over the last 10 billion years. Thus, it was confirmed that star formation has slowed down. In other words, the universe is becoming increasingly colder and more dead. Because as the universe expands, the distance between stars, planets, and even galaxies increases. I want to show this to you again now with a balloon example. Let's draw two stars here as a representation. Watch this now. As the balloon inflates, the distance between these 2 points increases. Think of this on a universal scale. I mean, such a massive, rapid expansion is happening that the distance between stars is increasing very significantly. In fact, after a while, it reaches such a point that everything breaks away from each other. Almost no usable energy remains, and all the stars go out. The universe approaches absolute zero and freezes. This is called heat death. Let me give you an example so you can visualize it. In the very distant future, new stars will almost never be born. Those bright spots that fill the sky today will start to go out one by one. Galaxies will drift so far apart that each will be buried in its own darkness. Only cooled white dwarfs, neutron stars, and black holes will remain. When enough time has passed, they too will slowly evaporate in a process called Hawking radiation. Eventually, everything we know as matter will turn into a very weak and cold energy radiation scattered into space. Neither new stars nor new stories will remain. Just a dark universe that is getting colder and colder. But what about the breadth of the universe? So if that hidden force is gradually weakening? I'm talking about dark energy. Well, very recently, physicists named T, Lu, and Q from Cornell University published a new model that addresses this very question. Now, this model could change the whole scenario. First, they asked this: can we explain the universe's expansion rate with the assumption that dark energy remains constant? If it can't be explained, then dark energy might be changing over time. We already have measurements regarding the universe's past. For example, we've been recording data like galactic redshift and supernova brightness for years. The wavelength of light from a galaxy stretches as the galaxy moves away from us. This phenomenon is called redshift. The more it is shifted, the faster that galaxy is moving away. So redshift gives us information about the rate of expansion. We can also get ideas from certain supernovas. So the team at Cornell took this data and plugged it into computer models. And they sought the answer to this. Does this data fit a model where dark energy weakens over time better than a model where it's constant? Remember how we talked about the struggle between dark energy and gravity at the start of the video? Well, this new study says that even dark energy might actually consist of 2 parts. What causes the universe's accelerated expansion today is dark energy that appears positive overall. We can divide this total into 2 parts. First, a region whose energy decreases over time. This is called the axion field. You can think of this field like a ball left on the side of a hill. Since it's high up at first, the potential energy is very high. As it rolls down, that energy decreases. The energy of the axion field is also slowly dropping over cosmic time. So the driving force accelerating the universe today acts like the energy of this ball rolling from a height. As time passes and the ball goes down, this driving contribution also gradually weakens. The second is a very weak but constant energy woven into the fabric of space, the cosmological constant. In the standard cosmology model, this constant was assumed to be positive, so it was seen as a force constantly pushing the universe outward. But this new model says the data shows this cosmological constant might actually be negative. The currently dominant positive energy field, the axion field, is suppressing this negative energy. Therefore, the universe is still expanding at a rapid pace. But according to the model, after a while, this field's energy will weaken and negative energy will dominate. You can think of this negative cosmological constant as a very loose rubber band wrapped around the universe. Now, I couldn't find a rubber band at home, but I'll use my daughter's hair tie here. Let's put the hair tie around the universe like this. Of course, it's not very loose, but in reality, this band is so loose that the energy pushing the universe outward seems to be winning the game for now. But what happens if this energy weakens after a while? The band starts to stretch and gradually takes control of the situation. Then the universe gradually shrinks. And finally, bam! That tragic end we call the Big Crutch. In this new study, physicists also provide a timeline for the end of the universe. But don't worry, this isn't a timeline that really concerns us. In fact, it doesn't even concern our great-great-great-grandchildren, because there's still nearly 20 billion years left for this to happen, folks. According to calculations, the total lifespan from the Big Bang to the Big Crunch is roughly 33 billion years. Let's think of the entire lifespan of the universe, from the Big Bang to the possible Big Crunch, as a 12-page calendar. Let each page be roughly one cosmic month. According to this model, the total lifespan of the universe is 12 months. So what is our current age? 13.8 billion years. This corresponds to approximately the 5th page of this calendar. So the universe hasn't even reached the halfway point of its own life. If we tried to place a human lifespan on this giant cosmic calendar, our 70 to 80 year life wouldn't even be a thin, barely visible line drawn with a pen on those 12 pages. So on one hand, we're talking about the multi-billion year fate of the universe, and on the other, we realize how humble our place is within this giant cosmic calendar. In summary, the universe is currently 13.8 billion years old. If this model is correct, the universe has completed 42% of its life, and there may be a little less than 20 billion years left. According to the model, the universe will expand for another 11 billion years and reach its maximum size. In the remaining 9 billion years, it will gradually collapse inward. Okay, we now know the end of the universe for sure, along with its timeline. Is that really so? Of course not, because that's not how science works, folks. Yes, this model is a compelling scenario that fits current data very well, but it's not the only one. The scientific world still leans closer to the idea of heat death. Some models suggest dark energy never changes, while others claim the effect gets even stronger over time. So we still don't know the definitive fate of the universe. We have scenarios before us that try to explain the same data in different ways. This study at Cornell is one of the scenarios suggesting the universe will one day collapse inward. In the coming years, new data from giant projects like Euclid and DESI will show us more clearly which of these scenarios we are closer to. So, are the possible predictions about the fate of the universe limited to these? Of course not. For example, in some models, the intensity of dark energy increases so much over time that it becomes strong enough to tear apart not just galaxies, but stars, planets, and even the bonds within atoms. The fabric of space stretches step by step. And finally, a phase is entered where nothing can remain connected to each other. This is called the Big Red. In another possibility, the end of the universe is thought of more as a change in the laws of physics than an explosion. What we think of as empty space isn't actually empty. It has an energy level. Some physicists say this might not be its most stable state. If one day, at any point in the universe, there's a sudden shift to a lower energy, more stable state, the new vacuum state starting there could spread at the speed of light. And the rules for all the particles and atoms we know could change. So the universe doesn't vanish, but the physics we know suddenly transforms into a completely different universe. This is called vacuum decay. And then, of course, there are those who say every end is a new beginning. The Big Bounce. According to this model, the universe could bounce back after a big crunch and start over with a new Big Bang, and this cycle could continue forever. All these scenarios have one thing in common. They all talk about unimaginably distant scales. We're talking about billions of years. Whichever scenario turns out to be true, none of them will directly affect our daily lives. But I think the most interesting thing is this. While we can't even predict the end of our own lives yet, we can make calculations about the end of the universe. While our own hourglass continues to run on one hand, we're trying to imagine the hourglass of the universe on the other. Perhaps this is one of the strangest features of being a conscious being. We probably won't see the grand finale of the universe, and we have no chance of changing it. But we can be aware of our own hourglass, and by using the time flowing through it, we can change the fate of our own little universe.